Okay. So at first, as I said, okay, I want to switch to a further concept, which is known due to the local concept and therefore as a structure stress concept. So the structure stress concept is always related, or structure stress hotspot concept is at this side always related to welded parts. And due to this, at first I wanted to go there and just give some pictures of what are welding errors and how do they look like. Because yesterday we just had this slide, which was, I think, not really efficient, to see, okay, what really happened or how does look like a really bad weld seam. So, for example, we have here our steel plate. Okay, the steel plate, of course, here is really thick. And as you can see, due to the several layers we have there, some binding or lack of fusion occurred in the sublayers. So this would be something like this, that at this side you have several layers. The layers are not properly welded. And so you see here that at the end you have a lot of mess inside your welded seam. And of course, this welded seam does not really doesn't really handle fatigue loads, but also cannot really handle at the same time static loads. So the next one is the high porosity. So as you can see here, for example, in the weld seam itself, in the top layer we have there some pores which also have a size of 2 millimeters. And this, of course, is not a really proper welded weld seam, and also due to the quality management, you have to say, okay, please open again, do it again, and make a really nice and proper weld seam. So the next one, also again at this side, high porosity. So you can already see here, due to the black colors, and these are huge pores. But also at the same time, you have here some inclusions inside, and also some root failure at this side, and also on this side, as you can see here, the weld seam is going over the blade, and so at this side the crack also can appear due to the overlapping of the weld seam, and at the end, this weld seam cannot handle much loads, much cycles. So also, which many times appear, is open end cavity. So which is, so for example, you have here at the side the two blades are fixed together. So the weld seam gonna ends here at this part. And due to the movement and due to the welding, you have here several time you stay there, and due to the induced heat treatment, at the end you have some open end cavity. So the next one is, of course, here at this side, the inclusion, but also the binding error. And also here you can see the same, some binding error at the surface. So this is something which we had already in the pictures before. So for example, it can also occur for a butt weld. So for example, usually you have at this side, the butt weld looks like this, but for example, there can be some weld material which gets over your welded part, and at the end you have here some overlapping, and this is some binding error at the surface. And for example, you can easily see this by dye penetration inspection. So this is just a color you spray there, and at the end you see, okay, how proper is the connection at the surface. The next one, of course, many undercuts. So as you can see here, we have here our welding part, and on this side we always have some undercuts, so there is some loose of material. There are always a lot of notches on the weld toe, and this of course is something we don't want to have into our welded parts, and so this is also open again and weld again. So the next one is also something I think which can occur many times, is some poor restart. So you start, for example, the welding from this side, and then you move again, and you start at this point to weld again. And so here at this stage you have a lot of material, and this is a poor restart, so you have a lot of material, and of course this is something which leads at the same side to a stress increasement, and at the end to some failures. So but also this is something we usually we don't want to see, and we have to fix due to the quality management in our welded parts. But also at the same time we have here some notches outside of the welds. They are also called weld imperfection or weld misalignments. For this I already showed yesterday some drawing which look like this. So usually we have here some different misalignments. So this is, for example, the axial misalignment and the angular misalignment. So the axial misalignment is something which, of course, results to a moment, and the angular misalignment at the same time also results to some further stresses, but also moves the specimen into this direction. So how does it look like? For example, here again a picture. So we have here some plate, and this plate, of course, is on a little bit lower. So as you can see here in the cutted version, we have here our ideal line, and the ideal line of our specimen at the same part moves in this direction. So at the same time, of course, if we have some tension there at the local specimen, it's gonna have some higher stresses as we would assume usually. So, and about this weld imperfections, so the two we have here, this is something which is, for example, included into the structural stress concept. So how does it look like? This is a drawing you usually can find in IIW or something else. And so we have, for example, here our specimen. Of course, we have our weld seam, and then we have different stress estimations. So our nominal stress concept, as we already have or done until now, is something like a constant stress value. So just sigma nominal is F over A, and but due to failure at this level, we also can measure some stresses which have an increasing effect onto our fatigue life, and decreasing on the fatigue life, increasing on the stress range. And so therefore, in the guidelines, there exist different extrapolation rules, and these extrapolation rules are defined due to the measuring of strain gauges, but at the same time are also referenced to the numerical analysis. So, for example, this is something if you want to look there and go into literature for structural stress concept, hotspot concept, you're always going to find here the information due to the extrapolation rules. And no, there's the wrong, wrong order of the pictures. And therefore, for example, you usually have two different types of hotspots. So, for example, the hotspot A, you see here, it is always in the range of a white plate. And so you have here no influence of the edges. The type B, you have an influence of the edges. And so you have also there some steeper gradient. So this is why you have at this side a nonlinear and a linear extrapolation to see, okay, for a steeper gradient, you have to use the nonlinear. For some type A hotspot, you can go for linear or also for the nonlinear. So there is no really benefit of both. So, and so this is I would say the main idea behind this concept, so that you say, okay, in the testing you can apply there some strain gauges, and at the same time with the strain gauges you can measure the increasing of the stress range. So you can also at the same time have some other stress ranges due to, for example, nominal stress, but also in the calculation, so in the later stress assessment, you also have to get somehow this information into a structure. And also, what is a benefit somehow there, that you can say, okay, you see about the stress transfer, you see about the load transfer in your system, but at the end, somehow you have to find an estimation which is including the real situation. And of course, in the preliminary design, there is no issue that you really can know about this, especially in civil engineering. So this is always something which is between, I would say, between good estimation and at the end some approaches which you can go in a step further. If you have more information about your structure, if you know more about your structure, then you can go there and see, okay, what misalignments your detail at the end can handle. So, and also in the investigation itself, there are some different model types you can use. So the simplest one, of course, is a beam model. So the beam model would look like the same as we have here. The shell model, of course, can handle, for example, a larger structure. So you can also go there, model some joints, model some girders. So for example, some orthotropic bridge girders or something else. And of course, the most time-consuming, but also calculation-consuming, would be the volume models. And therefore, you also can just estimate some strain gauges on your side, and at the end with the calculated strain gauge stresses, you can recalculate your stresses. So, and for example, if you go into a document called the IW, document 1823-07, there you can find, for example, some simple beam models which look always like this. So you have, for example, here this small drawing, and therefore you get a Km. So this is also a structural stress concentration factor. And so this part just gives you the amount of increasing due to a linear elastic calculation. So, for example, you know about your thickness T, and also the axial misalignment E, and about the lengths L1 and L2. So at the end, due to the supporting, so stiff or fixed or simple supported, you can choose here for a Km, and at the end get an information about the stress increasement next to your joint. So, How would it look like in an experimental investigation of the hotspot stresses? So for example, here, this is the linear extrapolation rule. So you have here the thickness T, and you just apply your strain gauge next to the value at a distance of 0.4 T and at a distance of 1.0 T. So what is the thinking behind this? That at the point of 0.4 T, all influences which result out of the weld shape, so also of the notch which is next to the weld shape, is already gone, and you just have here the increasing of the imperfections, of the misalignments next to the weld seam. So the same, of course, for the nonlinear extrapolation rule. Here, some different distances a little bit, 0.40, 0.19, and 1.40. And so these rules have been somehow investigated for for hollow beam sections. So this is some concept which results mainly from the offshore structures. And therefore, now it is, there is, I would say, the experience somehow or the idea to transfer this to simple plate structures, where you can say, okay, the plate structure at the end is connected in, for example, a rectangular or in an axle with an angle between. And so with this information at the end, you can give some more information due to your welded port and due to the fatigue assessment. But the basic rules always at this side have been done for hollow sections, and therefore, I would say the informations about some infections or some misalignment next to the weld too are not as important, because you have more influence due to the sections, how they integrate, how there are the notches defined, and so further. So how does it look like? So for example, we did it for some aluminum alloys in our case, and we have here the nominal stress approach would be at the same side, would be the orange line. So here we just calculated F over A. At the same time, we used here some data from a scanning system, and so we could increase here different steps just by the beam system, so some simple beam system, and also some stress analysis due to some further volume models. And what we're missing here is actually the strain gauges. They have to be added in the next lab, but this was not yet done. So as you can see here, it's just the increasing you get here for a simple butt welded joint, and at the same time the misalignments we had there have been around 0.5 millimeters to 0.8 millimeters. So at the same time for a 10 millimeter plate, really small, but already you can see the benefits you're gonna get there due to some structural stress concept. So, but also, you get a better approach, but also at the same time, you have to know more about your system, more about the tools you're gonna use. So, for example, this is also some small modeling, just a shell model of this joint, so just of the butt joint. So at the end, it is just two plates, two shell models combined and designed, and at the same side, we used here different definitions of the gap. So at the first side, we used some contact modeling. No contact. some kinematic couplings, and the kinematic couplings at the end work pretty well. But at the same time, we try to use here just a simple shell model. And the interesting part was here, if we just switched here the thickness of our shell model. So at the first step here, we had for this shell model element thickness of 10, which is the same as the two blades. So we got here the results which pretty fit to the estimated stresses we wanted to have. And so we got here a damage factor of 0.81. But on the same level, we just increased the thickness of this element here, so twice, so from 10 millimeters to 20 millimeters. And at the same time, due to this, we got at this side a lowering of our stresses. And so due to the lowering, we could also handle more stresses. So why is this happened? So if you go for example, numerical analysis, we have here our information about our shell element. And the shell element is always defined, for example, for a simple definition. So for a linear element, we have at this side 4 nodes. And the 4 nodes are always evaluated not really on the element nodes, they are always evaluated on the Gauss points. So this is the points of integration for our elements. And at the end, the results our program is delivering is always for the structural node at this part. And this node is influenced by this element, and also the two elements which have a thicker size. And due to this, we have here a mean value of all 4 elements. And so due to this, we have here the lowering stress. And so we have here the decreasing of the structural stress, which at the end does not really fulfill our estimations. So for example, as you can see here on a really small example, just on how you choose, for example, the combination of the joint, you have a high influence on the stresses you're going to calculate. And so you have really on this side to be sure on what you're going to do, and also how you're going to use your numerical tools. So just a short overview, and then I go to the example. So what are the advantages of the hotspot stress concept? So the investigation of the notch detail, which are not included in nominal stress concept. So for example, for some combinations of welded joints, you can get further information and therefore get in a, for example, if in the design or also in the situation of testing more information about what will going to happen, what are the stresses which going to appear. Then also the load transfer in the system can be analyzed, for example, regarding to different modeling in global models and also submodels. And there are also higher notches, higher notch classes can be applied. This is something I show later. And of course, the disadvantages, of course, are the results are related to the experience in the numerical investigation, and also the types of elements have an influence on the structural stress. So, for example, if you go and calculate the same system and you just switch the definition of this of the element of the shell element, at the end your results gonna be different, and so at the same level, you have influence which are not just due to the modeling, but also due to the numerical system or the numerical simulation tool you're gonna use. So, for example, if you go in your office and at the same time you have, for example, in the university, you tried something, you have a good simulation, a high-end simulation tool, you go to the office, maybe you have a really basic tool, and at the same time, the results would not be the same, just due to the definition of the elements. So, again, some questions to the sport. So, just to get a feeling or how to get an idea how the calculations end up, I did here in the Excel sheet a small calculation for the B model. So again, sorry. So again, just to have in the background the idea of our structural model, how it looks like, what are the parameters we have there. So the parameters at first is of course our E1 or and E2, and then our distances L1, L2, and the T, and of course how is our supporting situation. So in this case, I just choose a fixed support to have a easy amount. So if we now go into the IW or the basic or the primer literature, where we also can find these values here. You just gonna calculate it here. So we have here our 1. This is just the basic value, which is just the linear elastic situation without any misalignment. And then this is just the increasement due to our misalignments. So at the end, lambda plus lambda times E0 times M minus L1, L2 times TL. So, sorry, the E0 is here the E1, in case of questions. And so at the end, for our system, as I have chosen here, with a misalignment of 0.5, we have an increasing at the end of 1.04, which is not as much. It still acts on our system. And also the angular misalignment, the same. Here we have some information, some further information, which result in the movement of the joint due to the tension forces. And so this is something as a factor at the end, which is getting to 1. If you have a huge distance due to the joint. So at this part, this effect mainly acts for small specimens, for small distances in the structure itself. And so you have here at this time for the E2 of 1.2, an increasing of 1.02. So these are just due to the two different effects, the structure stress concentration factors, and this structure stress concentration factors are at the end just summed up. So we get here at the end 1.063. And so at the end, for example, we had for our detail before, a notch class of 80, and due to the increasing or due to that we take into account our misalignments on the side of the applied stresses, on the structural stresses. We also have here some increasing of the resistance stress of the notch class. And so, for example, for a nominal stress amount, we had here 80, and now we have here 100. So, and as the same before, for the modified structures, modified nominal stress concept, this factor at the end would be also applied on the structure stress range. So, okay, so far to this modeling, to this concept, I would say let's go for the break, and afterwards I continue with just some basic steps in the in fracture mechanics, and therefore it's just the preparation for Monday, because on Monday I will go a further step to the FID diagram, which is at the end a small diagram which at the end gives you some information about can your structure resist for some notches due to cold temperatures or also high temperatures. So at this step, just for now, I think we're somehow complete with the design curves, with the design assessment in fatigue, and now in the next step, go to some fracture assumptions. Okay, so see you in around 20 minutes, and then continue there.